Thank you for inviting me for this conference and presenting this research. I'm going to talk about the dynamics of a standing meander of the subantarctic front diagnosed from satellite altimetry and the long stream anomalies of temperature and salinity. This research is done by myself, Helen Phillips, Nathan Bindoff, Steve Rintel, and Annie Foppert. The motivation for this study is basically the ACC has several regions where the flow interacts with topography. Kerguelen Plateau, Southeast Indian Ridge, and the Macquarie Ridge, and downstream of the Drake Passage. And why are these areas so important? Well, the volume transport has been relatively constant of the ACC, although an increased wind stress over the last few decades. So the volume transport has been constant, and where the flow flows over rough topography, you see these standing meanders. And these standing meanders, they steepen or flex when the current gets stronger. And when the currents get stronger, you get these instabilities, barotropic instability, baroclinic instability, and they lead to momentum dissipation. And this momentum dissipation can also lead to heat transport to Antarctica. So this is in short why we do this research. So what have we done? We've looked at the observations of a standing meander, and we've analyzed the temperature and salinity structure by making like a graphous empirical mode of the CTD profiles, and we calculated the long stream anomalies in the meander. We've looked at the velocity and vorticity structure, and we've coupled the anomalies to the dynamics. So what was our survey? So our hydrographic survey was southwest of Tasmania in the subantarctic front, between the, so just downstream of the Southeast Indian Ridge. We had like 99 CTD profiles and about 11 transects that went from south to north and north to south through the front, and they went down to about 1500 decibar. At the same time, there was also a repeated SR3 line that went from north to south through the front. So these SR3 lines you see here in the front, on the top, so temperature and salinity, you see that north of the front, the isopycnals are relatively horizontal, and then in the front, you see that are indicated by these gray vertical lines. You see that there's strong temperature, horizontal temperature gradients, and steep isopycnals, and also in the salinity. And what we did with all the CTD profiles, we tried to kind of like get a cross-stream average of a transect. So that's what you see in these. So this is a sort of an average field of all the transects, of all the profiles in the transect. And what we did was calculating the anomalies by subtracting like each transect, the real fields minus this gem field, and then you get a long stream anomaly. And we've calculated these anomalies on isopycnals. So they are not due to heave, that those kind of anomalies we've divided from the anomalies on isopycnals. So you see purely the anomalies on isopycnals. So in the top four panels, you see the transects going into the trough. In the middle panels, you see the transects in between the trough and the crest. And into the crest, you see the bottom four panels, you see the transects into the crest. And we've divided the anomalies sort of like between 27.3 and 26.8. We're not looking at the mixed layer. And between 27.3 and lower, which we call the lower water column. So the upper water column is between 26.8 and 27.3. So when we look first to the upper water column, then we see that there is a progressively cooling from the trough in between, and then a warming again into the crest. Whereas if we look at the lower water column, so below 27.3, we see that there's a constant from cool to warmer and more warmer. So that's kind of the observations that we saw. So now we will talk a little bit about the gradient wind balance, because when the ACC is mainly a zonal flow, you see that the balance is basically a geostrophic balance. But here we see that there's an additional term in, so this would be the geostrophic balance, and then this is additional term, which is the curvature term. And the curvature term is basically caused by the curvature of the sea surface height contours. And what we've done is, and when you take that extra term into the balance, you basically get an extra force, like the centrifugal force, you take that into account. And that centrifugal force causes that there is a smaller flow velocity in the trough and a larger flow velocity in the crest. And this is an ageostrophic contribution to the flow. So normally the geostrophic flow is divergence free, but because this is the flow speed. And so when you see that the gradient of flow speed, you see that there is a current sort of against the main flow in the trough and with the main flow in the crest. And then again here in the trough, you see that the ageostrophic flow is against the flow. And this is the ratio that we plot is a sort of is another form of the Rossby number. And so it basically says how important this curvature term is to the Coriolis term. And so because the ageostrophic component causes divergence, so we're seeing that basically here by the continuity equation. So you see that the WdZ normally dUdx plus the Vdy plus the WdZ is 0. So that's a continuity equation. But now you see that these ageostrophic components cause this dWdZ. So we now know kind of like this term, and the other terms we could also calculate from a satellite altimetry. And normally in the ACC, the attraction of relative vorticity is balanced by the attraction of planetary vorticity. But in a standing meander, you see that this vortex stretching is balancing the attraction of relative vorticity. So this is the attraction of relative vorticity, and it's the attraction, and it's the vortex stretching. So these two are quite balancing. The attraction, the local time derivative of relative vorticity is quite small, and the planetary vorticity is also quite small, as you see. Yeah, so now we try to couple these anomalies to the dynamics. So we said before, we take here an average along the section, and so we saw this between 26.8 and 27.3. We saw this cooling from the entering the trough, exiting the trough, and then you see this warming entering the crest again. And in the lower water column, you see this cooling progressively getting warmer. We've averaged this for the upper water column and the lower water column by the orange and the blue line. So the upper water column is the orange line. So you see this warm anomalies causes a cooling, and the warming causes cold to warm anomalies. And in the lower water column, you see these cold anomalies getting progressively warmer, so they're continuously warming. So how do we relate this now to the divergence and the convergence? So when you're taking the first difference of the temperature anomalies in the upper water column, then you see that there's a cooling when this is negative and a warming when this gets positive. So you have negative, predominantly negative values when there's convergence, and then when there's divergence, there's predominantly positive values. And then the lower water column anomalies are explained by this rotation of the velocity vector with depth. So when from deep to shallow, when there is a clockwise rotation of the flow from the deep vectors to the shallow vectors, then you, from the deep velocities to the surface velocities, then you call that backing. And then there is cold advection of water and downwelling. Whereas if you have anti-clockwise rotation of the flow from the deep velocities to the surface velocities, then you have an anti-clockwise rotation of the flow, which is called veering and leads to upwelling and warm advection. So what is the takeaway message? Well, we see that the ACC can basically be divided in two regions. Regions with a relatively flat bottom, which is mainly in geostrophic balance, and divergence free, and so the ACC is the barrier for cross-frontal exchange. And then you have regions where the flow interacts with topography. There are meanders, which are in gradient wind balance that create zones of divergence and convergence and cause cross-frontal exchange, and momentum can be dissipated by bottom form stress or deep cyclone. Thank you for listening. There are questions?